This is the 16th lecture of the series and the second lecture on the excess carrier concentration. In the last lecture we saw the various sources of excess carriers and then we discussed the concept of injection level and quasi-Fermi level. We began a discussion of the parameter called the lifetime using an example that is shown here. So this is a transient situation that we are going to discuss. You have a semiconductor on which the light is falling and a voltage is applied so that a current flows. Now we explained the characteristics using this figure. The light intensity is switched on suddenly at some instant, then the intensity is maintained constant over a period of time and then it is switched off. The generation rate rises suddenly, it follows the same behavior as the intensity, and the resulting current that flows in the circuit, okay, however follows this particular shape. We have explained the various regions and we have said that here the excess generation and recombination rates are 0, R dash and G dash stand for excess generation and recombination rates. They are 0, this is the equilibrium state. Then there is a state in which although the generation rate has increased suddenly here, the recombination rate cannot rise immediately because the carrier concentration rises slowly and then it reaches a steady state when the generation rate is exactly balanced by the recombination rate. And then when you switch it off, when you switch the light off, the excess carrier concentration starts decaying. Now this is because even though the generation rate G dash has become 0 here, immediately when the light is switched off, the recombination rate R dash does not become 0. So it follows the carrier concentration and that is why you have a decay. The decay follows this particular law, d delta by dt is equal to minus R dash. On the other hand, the rise here follows the law d delta by dt equal to G dash minus R dash, that is the net generation rate. So always the rate of increase of excess carrier concentration depends on the net generation rate, okay. So here also this is the net generation rate, but since the generation rate, excess generation rate is 0, it is only the recombination rate and that is causing the decay. Now let us proceed further from here to discuss the concept of lifetime. Let us look at this particular situation, that is the decay. It has been observed that if the intensity of light that is falling here is small enough so that the injection level in the sample is low, then this recombination rate R dash can be written as delta by tau, where tau is a constant, a time constant, delta is the excess carrier concentration, meaning that the excess recombination rate is proportional to the excess carrier concentration, okay. Under low injection level, this time constant here will be independent of this excess carrier concentration. So tau is independent of delta for low level. In other words, R dash is proportional to delta under low level conditions, that is the meaning. So under low level conditions, the analysis of the device is simple and we are going to concentrate on the low injection level. So we can therefore write this equation d delta by dt equal to minus R dash as d delta by dt equal to minus delta by tau, this particular time constant tau. So that is the rate of decay. Please note that we have emphasized this in the last class. We are assuming that the excess carrier concentration is uniform throughout the volume and this rise of the concentration or the fall of the concentration is not because of any net input or net output of holes from any of the regions. okay, which means there is no flow of carriers. So we have neglected any carrier flow. Carrier flow is assumed to be 0. So this rise and this fall is only due to either generation or recombination. So under such situation, when you have only excess recombination present, this is the law. Let us try to interpret this time constant tau. The solution of this equation clearly is delta equal to the initial excess carrier concentration delta into exponential of minus t by tau, where delta, this is nothing but the value of this delta at t equal to 0. Now once we know that this is a solution, now we can interpret this time constant tau as the average lifetime of the excess carriers, okay. It is the average lifetime of the excess carriers. It is also called the average lifetime of the minority carriers. So we will show why it is to be called the average lifetime, okay. But first let us write down what are the two names for this time constant. So average lifetime of excess carriers or minority carriers. That is tau. Now it is to be noted here that tau cannot be called the lifetime of majority carriers. So this point we will explain, okay, later. Now let us explain first why it should be called the average lifetime of excess carriers. Let us start with this. Now you see from here that since the rate of the decay of the carrier concentration is exponential, the average time of the lifetime of the carriers in a exponentially decaying population. What is the average lifetime of carriers in the exponentially decaying population? Now this can be obtained using the following formula. So average lifetime of a particle in a decaying population is given by integral T d delta by integral d delta, where delta is varying from 0. Delta is initially capital delta and finally it is 0, okay. So please understand this formula. This is your carrier population that is decaying, this is delta, this is delta e power minus t by tau, and this is the time axis, okay. So for this particular decay, if you want to know the average lifetime of carriers, then it is given by this formula. So delta is the value of the excess carrier concentration at t equal to 0, and then this is at t equal to infinity, okay, because it is excess carrier concentration is falling to 0. This is excess carrier axis. Any such decay implies that all the carriers in the population do not have the same lifetime. This is clear, because if all the carriers were to have the same lifetime, then the carrier concentration would stay constant for that amount of time equal to lifetime, and then it would suddenly drop to 0, because all the carriers will get killed suddenly. But the very fact that it is gradually decaying means that all carriers do not have the same lifetime, and therefore we have to talk of an average lifetime of the carrier in this population. Now how do you interpret this formula? How do you get this formula as the average? This can be understood using this diagram, where I am going to show an approximation of this decay as something like these steps, okay. So this is delta versus t. Let us say this is delta 1, this is delta 2, and this is delta 3. This is T1, this is T2, and this is T3. This is T equal to 0, and this value, initial value, is delta. So what does a figure like this imply? It means that delta 1 excess carriers have a lifetime of T1. So after T1 duration, delta 1 carriers have got killed. That is why the excess carrier concentration has fallen by this delta 1. Then after another time T2, delta 2 carriers have been killed. Therefore the excess carrier population has fallen down by further delta 2, and so on. So remaining delta 3 carriers have decayed at the end of T3, which is the lifetime of these delta 3 carriers. So T1 is the lifetime of delta 1 carriers, T2 is the lifetime of delta 2 carriers, and T3 is the lifetime of delta 3 carriers in this population of delta carriers. Then what is the average time for which a carrier stays in this population, or the average lifetime of carriers? It can be written as T1 delta 1 plus T2 delta 2 plus T3 delta 3 divided by delta 1 plus delta 2 plus delta 3. So that is a weighted average of the lifetimes of individual populations in this decay. So this is the average lifetime, tau, T average. Let us call it as T average. This is average lifetime of carriers in this population. So it is evident that this is nothing but, you can write it generally as sigma Ti delta I by sigma delta I. Now if we go on reducing this size of these steps, okay, and we adjust this particular step like distribution, you will get this exponential distribution, okay. And therefore in such a limit, when each of these deltas become very small, delta I can be replaced by d delta, and the Ti is replaced by T. The summation sign is replaced by the integration sign, okay. So this summation is again replaced by integration, and so that is how you have this equation for the average lifetime of carriers in this decaying population. Okay, now this is nothing but integral T delta integral T d delta divided by delta with a negative sign. So since the negative sign is there, I will change the limits and make it 0 to delta, okay. So the denominator is minus delta, which I have put as delta, and I have changed the limits of the numerator. So this is the equation. Now I will leave it as an exercise for you to show that when you replace T d delta by the expression obtained from here, okay. So that is T into d of delta e power minus T by tau integral by delta. So from 0 to delta. Since this is a function of t, what you should do is that finally you will get this also as a function of t, and when you do the integration, therefore you will have to change this limits as delta is equal to 0, this is infinity, t equal to infinity, and delta equal to capital delta, t is 0, okay. So this is the equation, and one can show that this is equal to tau. So this is left to you as an exercise to show, and therefore the average lifetime of carriers, okay, in an exponentially decaying population is the same as the time constant of the exponential, and that is this tau. That is why we interpret this tau as average lifetime of excess carriers. Now why do we call it as average lifetime of minority carriers? That is another name to this. Now this is because we know that the minority carrier population is approximately equal to the excess carrier population, because minority carrier population is so small that even if the injection level is low, right, the carrier concentration of excess carriers would almost be same as carrier concentration of minority carriers. Minority carrier concentration is always disturbed and is almost equal to the excess carrier concentration. That is why we can also call it as lifetime of minority carriers. However, we cannot call it as lifetime of majority carriers. That is because majority carrier concentration is not exactly equal to the excess carrier concentration. In fact, under low injection level, the majority carrier concentration is not disturbed at all. Excess carrier concentration is much less than the majority carrier concentration. So you cannot call tau as a lifetime of majority carriers. This is important to understand. Okay. Now also note that the concept of lifetime, okay, as discussed here, is strictly valid only for low injection levels. This is because, as we said here, this tau is independent of delta only under low injection level, and only then you will get this exponential decay, okay, and only then you can show this tau as the average lifetime of carriers in the decay. So although the concept of lifetime is valid only for low injection level, in some modified form it is used under all conditions. Now the next step would be to theoretically show how you get an expression of this form for the phenomenon of excess recombination theoretically. Okay, right now we have said that this is observed, and from the observation we have introduced the concept of lifetime. Now we need to get an expression for this lifetime, okay, and show that indeed, okay, you will have this form of excess recombination if you start from theoretical principles. The first step in this is to first consider the various mechanisms of generation and recombination, okay, in different semiconductors. So generation recombination phenomena. Now we may tend to think that whenever an electron meets a hole, the recombination occurs. Now strictly speaking, this is true only in some semiconductors such as gallium arsenide. Wherever an electron meets a hole, a recombination occurs, or wherever an electron meets a hole, a recombination occurs, wherever in the semiconductor sample. On the other hand, it is found that in certain semiconductors like silicon, it is necessary that wherever when the electron is meeting a hole, it is necessary that there be an impurity or some other agency be present for the recombination to occur. So in semiconductors like silicon, the recombination will not take place in all regions of the semiconductor where electron meets a hole. So only near certain sites within the semiconductor, if the electrons and holes meet, recombination can occur. So therefore we need to understand this particular aspect in detail. Let us look at the generation recombination from the energy band point of view. So the process in which the electron recombines with a hole without the aid of any other agency. So whenever electron and hole meet, they are recombining. This is shown on the energy band diagram as shown here. So this is recombination, and the reverse of this is generation. Now this particular process of generation recombination is called direct generation or recombination. This is because wherever the electron and hole meet each other, they can recombine. So electron is jumping directly into a hole on the energy band diagram. As against this, the recombination in the semiconductors such as silicon, so this direct recombination takes place in semiconductors such as gallium arsenide. Okay, so example, gallium arsenide. So in silicon, the process occurs something like this. The recombination occurs when an electron jumps to a site that is called the impurity site or an intermediate level between the conduction and valence bands, and then it jumps down, okay, into the valence band. So the generation similarly occurs by electron jumping from valence band to this site, the impurity level or defect level, and then it jumps up, okay. So this is called indirect recombination. This particular process is indirect because the recombination occurs via an impurity level or defect level within the energy gap. Now physically this means that if this is your semiconductor block, there will be some locations in this semiconductor block where there will be defects or impurities, and these defects or impurities will have an energy level between the EC and EV levels somewhere in the energy gap. Via this particular impurity sites the recombination is occurring. So if the electron and hole meet at this site, the recombination will take place. Now there are some qualifications for the impurity or defect sites to act as recombination centers. Now what are those? An important qualification is that the energy level corresponding to this particular site which must aid recombination should be somewhere near the middle of the energy gap, okay. So you can see here that this level is somewhere near the middle. It is not necessary that it should be exactly in the middle, okay, but somewhere near the middle. Now why? This can be understood with the help of a simple analogy. So imagine that you have a channel, a narrow channel across which people want to jump. So you have a large number of people lined up here who want to jump across the channel. Now the channel is narrow, but it is not so narrow that all the people can jump very easily. Now you find out how many people are able to jump this channel. Now you want to create a situation where all the people would be able to jump. The best way you can do it is to introduce a step in between. So imagine that we have introduced a step in between here in the channel, so that people can first jump onto this step and then they can jump to the other end, the other side, other bank of the channel. Where would you locate this step so that the situation is easiest for all of the people? Now it is evident that if you locate this step very close to this end, then the effect of the step is not important, okay. The step is not making your job easy at all because you have to jump this long distance. On the other hand, if your step is close to this end, then also it is no use because you have to jump. First jump is easy but the second jump is difficult. So both the jumps should be equally easy, only then the situation is favorable. So which means that your step should be in the middle or at least somewhere near the middle, then all these people would be able to jump across easily. Now in a similar manner, the energy level corresponding to the particular impurity site which wants to act as recombination centers should be somewhere in the middle. In other words, these should be what are called deep impurities. So these are deep impurities, or they can be defects also. So let me not call them as impurities alone, we will call them sites having deep levels. Okay. So the energy level corresponding to these sites is deep. So only at such sites the recombination can occur. This is the indirect recombination. So it is evident that the rate of recombination in such semiconductors as silicon okay, where the recombination can only occur via deep impurity sites, the rate of recombination will be much less than in semiconductors like gallium arsenide, where the recombination can occur anywhere where the electrons and holes meet. So this has been found by experiment, that the lifetime of excess carriers in gallium arsenide is very low, meaning the recombination rate is very high as compared to silicon, where the recombination rate is much lower. Now we need to explain why this kind of recombination is not possible in silicon. Okay? What is the difficulty in having direct recombination in silicon? So to explain this particular aspect, we need to consider the momentum of electrons in the conduction band and in the valence band. So this particular diagram here shows the change in energy of the electron which is taking part in recombination. We also need to consider the change in momentum, because as we have said earlier, generation recombination phenomena can be treated as collisions among particles. So recombination can be treated as a collision between an electron and a hole, where both the particles are annihilated and the energy as well as the momentum therefore should be dissipated. So it should be given away to some other particle. Okay? So what is that particle and how much is the change in momentum? Because what is the change in momentum, that will decide to which particle the energy and momentum can be given away. So we now next discuss the momentum considerations, okay, in transition of electrons from conduction to valence band. So momentum changes during electron transitions. For this purpose, we need to draw what is called an energy momentum diagram. Okay, this particular energy band diagram, the momentum considerations are not shown. So we need to plot energy on the vertical axis and momentum on the other axis, and then we can understand the changes in momenta during transitions very easily. Now how do you get the energy momentum diagram of electrons in the conduction and valence bands? This is the issue. To understand this, let us start with the energy momentum diagram of, let us say, free electron. So free electron with zero potential energy. For this, the energy momentum diagram will be something like this. So this is energy, this is momentum, P is momentum. So this equation is E is equal to P square by 2m. This is a free electron, which means electron in vacuum, so it has only kinetic energy because potential energy is 0. Then you know that the kinetic energy can be written as P square by 2m. So this is the shape of the energy momentum diagram for a free electron. Let us see the diagram for a photon. For a photon, it is just a straight line, because the equation is E is equal to P the momentum into c, which is the velocity of the photon. So this is for a photon. Now in a similar manner, one can draw the energy momentum diagram of an electron in a periodic crystal potential. Please understand that when we are talking of electron in a crystal, it is electron in a periodic potential. So it turns out that this diagram looks something like this. So this is electrons in periodic crystal potential. Or periodic potential in a crystal. How does this look like? It is a somewhat more complicated. Let us draw it first and then we will give an explanation. So this is E. For electron at the conduction band edge, in some semiconductors the energy versus momentum diagram is this, and for the valence band, so this conduction band, this valence band. So in some semiconductors the diagram is something like this. So minimum of this particular energy momentum line is aligned to the maximum of the energy momentum line corresponding to valence band. Okay, that is what is shown here. This is true for some semiconductors such as gallium arsenide. Okay, so example, gallium arsenide. Whereas in some other semiconductors such as silicon, the picture is like this. So this is example silicon. So here what you find is the minimum of this energy momentum relation and the maximum of this energy momentum relation, minimum of the energy momentum relation for the conduction band and the maximum of the energy momentum relation of the valence band, there is a difference. Delta P. This is a picture in silicon. Now how do you get this kind of diagrams in semiconductors? Well, you know that electron in a crystal can be treated either as a particle or as a wave. When electron is treated as a wave, then for any travelling wave there is what is called a dispersion relation. That is frequency versus lambda relation. This is called a dispersion relation. For any travelling wave you will have a relation. Okay? If you have difficulty understanding this, please go back and see your physics notes a little bit. We will take this as a starting point. We will assume that this is known, that for any travelling wave there is a dispersion relation which gives you the relation between the frequency of the wave and the wavelength of the wave, lambda. Now by wave particle duality you know that the frequency can be related to the energy because E is equal to h nu, and the wavelength lambda can be related to the momentum because P is equal to h by lambda. So this new lambda relationship can be converted into energy momentum relationship. Okay, and that is how you obtain this energy momentum relationship for an electron in a crystal. Okay, please note that here this P is referred to as crystal momentum. and this is not the same as, for example, the momentum of a free electron. Okay. So this is the picture in a crystal. It is obtained from the wave particle duality relationship using the dispersion relation. So one must be careful in interpreting the momentum. For example, here the momentum corresponding to the energy is the same even though the energy is different, okay, in the conduction and valence bands. How can this happen? One may get a doubt, because if the energy is changing, the momentum should also change, right? But this is where you must know that we are talking of crystal momentum, and this is some kind of an imaginary concept. You are talking of momentum of a electron as derived from the wave particle duality. So therefore, once you understand this, then you will not confuse this momentum with the momentum that is written here for a free electron. Okay. So like whole is an imaginary concept, crystal momentum is a concept that is introduced to simplify the situation of wave particle duality. Okay. Electron is actually a wave, so you are looking at the wave as a particle, converting the wave nature into particle nature so that you can treat the collision phenomenon in a classical manner. So this means that in semiconductors such as this, when an electron undergoes a transition from conduction to valence band, it will not have any change in momentum. On the other hand, in semiconductors such as silicon, this clearly shows that when an electron makes a transition from the conduction to valence band during recombination, there will be a change in momentum, that is delta P, and this change in momentum has to be dissipated. Okay. So this momentum, this is the momentum delta P that will have to be dissipated in a recombination process. So here the recombination transition is shown like this. The generation will be exactly the reverse of this. Okay. You just reverse the arrow here and the arrow here, you get the generation process. Now in terms of this picture, one can explain why direct recombination is difficult in silicon. In silicon, if an electron has to recombine with a hole, the momentum has to be dissipated, and if you look at the momenta of different particles such as photon, the phonon, and other electrons and holes which are present, then it will be clear that this momentum cannot be given to a photon. Okay. It can only be given to a phonon or a particle, and then one makes a rigorous calculation of what is the possibility of the momentum being given to a photon or a phonon, and then one finds that unless a third particle is involved, this process, the probability is very low. We are not going to discuss this issue rigorously because you need to know much more amount of physics to understand this, but you will accept this as a statement of fact that to dissipate this momentum you need a third, an agency, external agency or a third particle, and it turns out that this deep impurity here, okay, or these sites where the it can be a defect or an impurity having a deep level, these kind of sites are very useful in enabling the electron to dissipate its momentum, okay, in silicon like semiconductors, that is, these are called indirect semiconductors. So this is the example of a direct semiconductor, energy momentum relationship in a direct semiconductor, the example of energy momentum relationship in a indirect semiconductor. So another thing that can be seen here is that in direct semiconductors there is no change in momentum, and therefore the energy that an electron has to release during recombination can be given to a photon. Okay. The momentum change, the amount of momentum that a photon has for any given energy is very, very small compared to that of a phonon or an electron. Let us see this. The momentum of various particles, photon, E is equal to P is equal to h by lambda, that is let us write in terms of, we want to write the momentum of photon and a photon and an electron for the same energy. So for a photon the momentum P is equal to E by C, the velocity. For a phonon the momentum is equal to energy E by V, which is the velocity of the phonon, which is much greater than C. Okay, so that is how you see that a phonon has a large momentum as compared to photon. This C is large, so the momentum is small, whereas the momentum of a particle such as electron, for example, in a crystal, okay, it will be given by P is equal to, you have to use P square by 2m is the kinetic energy. So P is equal to square root 2m into kinetic energy, where m is the effective mass. So this, we will assume that E is kinetic energy, so let us retain the symbol E here. So this is how one can estimate for any given energy the momentum of a photon, the momentum of a phonon and momentum of an electron, okay. And that is how one arrives at the conclusion that since the momentum of a photon is negligible and negligible change in momentum is involved here, okay, the momentum can be given to a photon, and that is why the radiative recombination is possible in gallium arsenide, okay. So direct recombination is possible and the direct recombination is radiative in semiconductors such as gallium arsenide, and using the same relationships one finds that the momentum of a phonon and that of an electron is fairly large for any given energy, and therefore one arrives at the conclusion that in indirect semiconductors such as silicon or in indirect recombination the momentum can only be dissipated to phonon or an electron, and the process of dissipation of a momentum to a phonon is aided considerably if a third particle is present, okay, near which the recombination occurs. This third particle or an external agency are the sites corresponding to which have deep levels. Incidentally, here this is the EC and this is EV, and similarly here this is EC and this is EV. Okay, so this is the energy gap, so this is also the energy gap here. This is why in fact gallium arsenide, based on this diagram one can explain why gallium arsenide and other compound semiconductors which have direct band gap, okay, this is an example of direct band gap semiconductor where the momentum change is 0 for the transition. So these direct band gap semiconductors are suitable for optoelectronic devices where you want to convert electrical energy into light. So light can be emitted when the excess carriers are recombining. On the other hand, in silicon light cannot be emitted, okay, because of this delta P associated with the recombination. So the recombination in silicon therefore is non-radiative. You cannot use silicon for emitting light, okay. You may be able to detect light, create excess carriers by illumination, but you cannot emit light through recombination of excess carriers in silicon. So in indirect band gap semiconductors light cannot be emitted, and therefore this cannot be used for applications such as LEDs, light emitting diodes or things like that. Now let us discuss the expressions for these recombination mechanisms and show that under low level conditions the recombination rate, the excess recombination rate will be proportional to excess carrier concentration. Let us start with band to band direct recombination. Here the electron is falling from the conduction band to valence band straight away. Now this kind of recombination depends on the concentration of holes and concentration of electrons. So you can write the recombination rate as R equal to a constant into product of hole and electron concentrations. We are interested in the excess recombination rate R dash, that is given by the recombination rate R minus the recombination rate under equilibrium conditions R suffix 0. So which can be written as alpha into P into N minus P naught N naught, where these are the equilibrium concentrations. Now here the P is equal to P naught, the equilibrium concentration, plus delta, that is excess carrier concentration, and N is equal to N naught, equilibrium concentration, plus delta, that is the excess carrier concentration. Please note here that the excess carrier concentration of holes and electrons is the same, that is why we are using the symbol delta. This can be simplified and we will obtain R dash equal to alpha into P naught plus N naught plus delta, this whole thing multiplied by delta. So what is happening is this P naught N naught product term is getting cancelled when you multiply these two. Now if you take an N type sample under low injection level, then the P naught is a minority carrier concentration, it can be neglected, and also delta is much less than N naught, that is the meaning of low injection level. So this equation can be approximated as alpha into N naught into excess carrier concentration. So finally we write the excess recombination rate is given by excess carrier concentration by a time constant, and this time constant is given by 1 by alpha naught. So this is the time constant of direct band to band recombination, and we can also call this as the lifetime for direct band to band recombination. So very clearly this shows that since alpha is a constant and N naught is the equilibrium concentration of majority carriers, this is also a constant for a material, and therefore the excess recombination rate is proportional to excess carrier concentration. So this is how one can derive the fact that excess recombination rate is proportional to excess carrier concentration in the case of band to band direct recombination. Let us consider another kind of recombination which is present, and this is the band to band Auger recombination. In this case an electron is falling from the conduction to valence band, and the energy and the momentum is being given away to another free electron whose energy increases. Now the energy can also be given away to a hole, in which case you will have a whole increase in energy. Okay, so what we have shown is for an electron it can also happen for a hole. So this is the Auger process, this is called an Auger recombination process. Now since here three particles are involved, that is this electron, the hole, and a third particle which is an electron here, it can be a hole also as we said. So therefore we can write the recombination rate in this case as proportional to P square N, that is hole recombining with an electron and giving the energy to a hole, or the hole recombining with an electron and giving the energy to another electron. So electron hole process and hole electron process. So R can be written as equal to a constant into P square N plus another constant into N square P. So we are assuming that the constants associated with these two processes are different, the hole process and the electron process. Now if you consider an N type material, then the above equation can be simplified to N square P, because P will be the minority carrier concentration, and so P square N term will be very small compared to N square P term. Now we proceed further and write the expression for excess recombination rate. This is given by gamma into N square P minus N naught square P naught. This is the equilibrium concentrations of electrons and holes. And as we have done in the case of the direct band to band recombination, we can simplify by substituting P equal to P naught plus delta, N equal to N naught plus delta, and cancelling out the terms, you will get this relation. This will simplify to this particular equation. So clearly showing that the excess recombination rate is proportional to excess carrier concentration for low level conditions. So the simplification that we are talking about is for low level conditions, and we can write this excess recombination rate finally as delta by a time constant, where that time constant is 1 by gamma into n naught square. So this is the lifetime associated with the Auger recombination under low injection level. So please note that while the direct recombination lifetime is inversely proportional to majority carrier concentration, the Auger band to band recombination lifetime is inversely proportional to the equilibrium majority carrier concentration square. Finally, let us take up another important process of recombination, that is the indirect recombination via deep level. Okay. So electron is falling into a deep impurity level or deep defect level, and then from that defect level it falls into the valence band and recombines with a hole. This is the process. Now the physics of this process is somewhat more complicated than the band to band recombination process or the Auger recombination, band to band radiative or direct recombination process, and band to band Auger recombination process, which we have just now discussed. So we will give here the result of the theory, which was given by Shockley, Reed and Hall. This is called SRH theory. So as per this theory, under low injection level, the excess recombination rate will turn out to be proportional to the excess carrier concentration and the concentration of the deep impurity or deep level, that is this. So this is n suffix I stands for impurity or defect. So we can write this in the simplified form as R dash equal to excess carrier concentration by tau, which is the lifetime for SRH recombination under low injection level, that is 1 by theta times Ni, the deep impurity concentration. This constant theta consists of a term reflecting the location of the energy of this impurity level. So it is to be emphasized that if the energy, this particular energy level is close to EC or EV, then the theta will be such that the recombination rate will be very low. So recombination rate will be high, or this impurity level will be effective in giving rise to recombination only if the impurity level is somewhere near the middle of the energy gap. So now in any semiconductor, the recombination rate will depend on all these three processes and some other processes also. We have discussed the three dominant processes. Let us see how all these processes contribute to the lifetime in n-type silicon. So in n-type silicon, as shown here, as you change the phosphorus doping, the lifetime changes from about a millisecond at 10 power 12 or very low doping to about 10 power minus 10, that is 0.1 nanoseconds or 100 picoseconds at about 10 power 20 per centimeter cube doping. So this is the curve representing the variation in lifetime as a function of phosphorus concentration. This lifetime is due to the direct recombination as well as due direct band to band recombination as well as band to band Auger recombination. So two processes together contribute to this lifetime, and it also contains a little bit of the effect of the SRH lifetime or recombination through deep levels, because as you increase the phosphorus doping, some defects are created unintentionally in the crystal. So some component of the SRH recombination is also present in deciding this particular curve. Now when you dope this n-type silicon with gold, which is a deep impurity, then the lifetime falls drastically, and as you can see by a straight line behavior, the lifetime falls as inversely related to the gold doping concentration, and the fall in the lifetime is tremendous. You can see, for example, at 10 power 16 from about 10 power minus 4 it falls to 10 power minus 8, okay, so 4 orders of magnitude. So this is how gold introduces the deep level and creates the Shockley-Reed-Hall recombination starts dominating, and that reduces the lifetime like anything. This data is obtained from these references in Solid State Electronics 1987 and from a book on semiconductors published by John Wiley in New York and authored by Wolf. Finally, we will discuss the important concept of surface recombination. Any semiconductor at the surface has a higher recombination rate than in the bulk. This is because the surface is prone to impurities. Also, because the surface represents a disruption in periodic atomic potential, a large number of states are created within the energy gap in a region near the surface. So if you take the energy band diagram of this region near the surface, you will find that within the forbidden gap you have a large number of states. This is the reflection of disruption in the periodic atomic structure. So there are a number of the states are near the middle of the energy gap, and therefore they will reduce the lifetime because of the recombination via deep levels. This is because of the SRH. As per the SRH theory, the recombination, whenever deep levels are present, the recombination rate is very high. So if you see the excess carrier concentration as a function of distance, one finds that the excess carrier concentration will drop as one moves closer to the surface. Let us say the surface excess carrier concentration at the surface is delta S. Then it can be shown that the excess recombination rate at the surface R dash S is proportional to the excess carrier concentration at the surface under low injection level conditions. So we will not discuss the derivation of this equation, we will just accept the result. So when you convert this proportionality into an equation, you will introduce a proportionality constant. Let us see what is the dimension of this constant. The recombination rate at the surface has dimensions of per centimeter square per second, where we are talking of per centimeter square of this area of the surface at which recombination is occurring. The excess carrier concentration has the dimension of per centimeter cube. So naturally the constant S will have dimensions of centimeters per second. This is the dimension of velocity, and that is why this particular constant is called surface recombination velocity. So the recombination at the surface, the excess carrier recombination at the surface is characterized by this particular velocity called the surface recombination velocity. Its value ranges from 10 to 10 power 5 centimeters per second. A low value represents a very clean surface, whereas a high value represents a very bad surface. Now towards the end of the discussion, let us see what are the topics that we have covered in the last two lectures. First, we discussed the methods of generating excess carriers. Then we discussed the concept of injection level. Then we discussed the quasi-Fermi level. We spent a lot of time on the important parameter that characterizes transient response, that is the lifetime. We discussed the various recombination phenomena such as direct and indirect recombination, which decide the lifetime in a semiconductor, and finally we discussed the aspect of surface recombination.